Good afternoon, ME 475 class. Today we're going to be presenting you on our final project in which we chose to test a wrench and several models of it. In overview, we're going to be going over the problem definition, some analysis that we did, and some conclusions that the group came to. Definition of the problem. The blue areas that you can see highlighted in pictures are fixed. They'll simulate a nut. The red area is where we apply the force to the wrench that simulate a hand turning it. Force components is split between normal and mixed. Normal is just in the y direction, mixed is in all three coordinate axes. Force magnitudes between max and average. Average load is standard use. Max is when someone's really trying to turn that and put in all the force that they can into it. Mesh size is 1 millimeter and hex dominant mode was used.
These wrenches were given a load and deformation occurred in all of them. These deformations weren't always to scale, but the max calculated by ANSYS was accurate. The largest displacement was almost 20 millimeters for the wrench with the smallest cross-sectional area, which is shown here. The picture on the bottom left was the multi-directional loading with a magnitude of 200 megapascals, and the one on the bottom right is the loading normal to the edge of the wrench. This wrench was analyzed to see how much material could be taken off to reduce the cost of production, but it failed. The wrench with the slightly less reduced cross-section had a total deformation of about 3 millimeters under maximum loading, which is equal to about 0.1 inches. This wrench only failed at the maximum loading, so it could be used in some situations and not break. The rest of the wrenches generally had a deformation under 1 millimeter, which would be almost negligible. For the material of the wrenches, structural steel was used, and the maximum tensile strength of this steel is 460 megapascals. For the wrenches tested, 9 out of the 10 did not fail under the average person strength. However, 4 of those 9 did fail at the maximum loading. The wrench with the lowest amount of stress is shown here, and this wrench had the thickness of the ends increased from 5.4 millimeters to 7 millimeters. The maximum stress was always in the neck of the wrench and would be the point of failure.
Difference in loading, normal versus mixed. With the normal loading, you saw symmetric both horizontally and vertically within the wrench. Highlighted areas within this would be that blue strip, which is the edge of the fixed point within the wrench in our model. If you look at that, there is symmetric on the left, asymmetric on the right, and that's the same for the loading. Other key areas are that interface between the handle of the wrench and the head of the wrench. With the asymmetric, you saw major stress points in opposite corners. With the symmetric loading, you saw an even distribution among all 4 corners. With shear stress, you saw similar effects and then add in a low point in the middle of the wrench head. That's not something we initially expected to see there, but after ANSYS analysis, it's an interesting thing to see there. Loading is similar between symmetry in those as well. Some questions that we came up with. Do rounded edges make a difference? How does width affect this cross-section? We found that typically rounded edges do not make a significant difference in performance of the wrench. Small changes in width typically do not cause any problems. In fact, there's probably room to cut down on the section of that, and major changes in the cross-section did significantly affect the performance of the wrench. In summary, we went over the problem definition, analysis, conclusions. Are there any questions for the group?